Well, welcome back. Very shortly, you're going to be taking a lab assessment, and that can be found in this area called Important Combinational Logic Circuits in your calendar. Touch the O and click that, and you'll get the study sheet, which you should print out before coming to the um, lab assessment. Now, just to give you an idea what you should be prepared for, you should be prepared to make calculations such as shown over here. There are two parts. The first part is a calculation that will show how to uh, uh, complete these written calculations, and there's going to be quite a few points associated with doing that. Then the laboratory part will be then involved with building some of these circuits, in particular the non-gate circuit, the decoder circuit, the multiplexer circuit, and also not shown on this sheet is a ROM circuit that you have to be prepared for. In addition, make sure you can program VHDL representations for any algebraic Boolean algebra expressions such as shown here. All right, let's go on to the subject for today. Read-only memories. We have covered some of this in an earlier class, but I'm going to review some of this. So read-only memory, it basically is a programmable truth table consisting of an n-bit address, shown in red here, and producing an m-bit data bit. Now, a typical thing that you might have, and we'll be showing examples, are with 3 address bits and 8 output or 1 byte of output. But it can be many bytes, such as 256 bits, for example. The way that this ROM works is that it uses a decoder and an encoder. Notice that the addresses are fed to the decoder and the data is taken out of the encoder. The purpose of the decoder is to select a word in the contents of the read-only memory. The encoder is to encode the representations of zeros and ones, which could either be fuses or charges, and that will then produce the data output. The size of this rectangle that you see here is m on the bottom and 2 to the n, and if n is equal to 3, that would be 8 high here. Of course, memories are much bigger than this in reality. The capacity is the number of bits that's in this blue rectangle, and that is the height by the width, or 2 to the n by m. And that's summarized with the formula over here. Now let's go ahead and look at some sample calculations associated with this, and also an iClicker assignment that you'll be given to complete. And let's go over here to our first description. Okay, so we have your diagram that we just described. And now we're going to look at making a calculation. So you see this red box here, we're going to make the calculations based upon knowing what n and m are. I'm going to do a sample calculation, and then you're going to have an assignment to do a couple more. So let's say that n is equal to 8 and m is equal to 32. The capacity is then going to be 2 to the 8. Let's go ahead and get this set up so I have my pencil. So 2 to the 8. And m is 32. That's 4 bytes of information. So it's a 4-byte word output. Now I'm going to express everything as powers of 2. And that calculation that you see can be represented by a power of 2 raised to the sum of those exponents, which will be 13. 8 plus 5. So that would be the answer, 2 to the 13 bits. But what is 2 to the 13 bits? That's hard to understand. So instead, we usually use some common formats, such as a K, a capital K, representing 2 to the 10. So let's break that up as 3 times 2 to the 3 times 2 to the 10 and use this K answer here. Now 2 to the 3 is going to be 8, and therefore the final answer in using this notation is going to be 8K. All right, so that's your sample calculation. I made use of this table here, and so you can make use of the table of 2 to the 5th is 32. That's going to be given. And here was my representation for capital K. Now that's to be differentiated from small k. A small k is equal to exactly 1,000, and that's different. And you'll see small k in some of your physics and chemistry classes. All right, now let's move on. Here's your first iClicker assignment. Now, what is an iClicker assignment? It's different than the polling that you've done, and I want to remind you how it's done. It was explained earlier. If you look at your, when you do your iClicker, you go to your smartphone, and if you bring up the iClicker app, on the bottom, you'll see 4 tabs, and the third one is going to be called iClicker Assignment. Now, the iClicker Assignment is different than a polling scenario because an iClicker assignment has a due date. That due date will be given to you on an email. It's not immediately afterwards like it is in a polling. So after we're done, I want you to or stop this video right here and go over and see if you can do this calculation. Here in this calculation, this first one, I'm going to ask you to make a calculation such as what I have shown over here. So in the blue box, what you would have written is 8K. In this calculation, n is 12 and m is equal to 4. So I want you to run this down just as I did before and make that calculation. So that'll be your first problem to do. Okay. Now go ahead and restart the video and let's go on to another problem. The second iClicker calculation that I'd like you to do is this one. In this particular case, I'm going to give you the capacity. I'm going to give you a capacity of 32K bits of information. And in addition, I'm going to tell you what M is. Now, the formula that you're going to use is the same as before over here. It's 2 to the n by m. However, capacity is given and m is given. I'm going to ask you to solve for n. All right. So if you make a change here, and you can solve what n is through an algebraic expression that I've given you some hints on how to do, go ahead and complete the calculation for your second iClicker assignment problem. I'll give you a second here to pause the video and go ahead and do that. Okay, let's go on now to continue with our class. Well, historically, 5 kinds of ROM implementations have been done. And this goes from the ones that were invented very early on in the I believe maybe as early as 1970, where the company would actually manufacture a ROM for you using a mask programming technique, all the way to the flash memories, which are the ones that you currently use and that exist in your smartphones right now. Here are some pictures of what some of those look like. You can also look up the encoding techniques. I have discussed this plus the earlier idea of memories and descriptions of these memories on an earlier occasion. But if you click this link here, it will show you the technique of building an encoder in these memories. All right. Remember, the decoder is necessary to select a word, and an encoder is used to hold information. The information can be held using techniques like the diode fuse array or a array that we'll be talking about that uses charges, so-called double gate MOS transistor array. So that'll come up here shortly. Next, we're going to talk to you about implementation of a decoder and an encoder using transistors and giving you two iClicker assignments to do, in addition to the ones that I've already discussed. A programmable read-only memory, which is one of the ones over here, is one that allows me to program them using fuses. In this um, circuit here, I'm going to explain the details here in the center, but let's go ahead and just show the inputs and outputs. I'm going to apply an address on the top, and I'm going to have 3 bits of address going from 000 to as much as 111, but I only show three cases, 0, 1, and in green, 2. I have 8 outputs, Y0, Y1, Y2, and then 5 more below it that are not shown. The idea here is I apply an address here, and I'm going to select one of the words here. So in this case, in red, I select this word. I'm going to select Y0. Or I should say it this way, this circuitry here will select Y0 in the encoder that's going to follow this. In the blue case, I'm going to select Y1, and in the green case, I'm going to select Y3. Now, all 3 cases are actually worked out here, but I'm going to do those individually in just for a second. But let me just go ahead and show you where this Y goes next, which is going to be in the encoder. So here's the encoder, and here are my red case, my blue case, and my green case. So selecting the first word, the second word, and the third word. And there are 5 more after this that are not shown. At the bottom here is the final results. Those final results are for the red case here. For the blue case, this is the 4 bits of output. And in the green case, there are additional 4 bits of output. All right, so that gives you the general scheme of how things are working. So let's go to the artboard, and I'm going to do the red case and a little bit of the blue, and I'll expect you to read the rest of it on your own. So here's the artboard for this case. So you can see here on the top, I show a starting position of applying an address of 000. I'm going to select the first word, which is Y0, and I'm going to deselect the rest of these. And these are, by the way, active high decoders. In between each of the Y0, Y1, and Y2 are differentiated by the positions of these transistors that are done. We'll find out they're actually in a counting position of 000, 001, all the way to 111 on the bottom, 111 on the bottom. Let's go ahead and explore the first case. If I apply a 000 in this case, then I'm going to grab a little bit of the red here. Through the double inverter here, I'll also have 000, and these are going down like this all the way. And I'm not going to show that any further. A 0 will touch this transistor here and turn it off, turn this one off, and turn this one off. Notice I'm using a red pen here, indicating I'm just doing the red case. This 0 here is going to turn this transistor off and this transistor off. And this 0 here, notice how that 0 is attaching to these positions here, are going to turn this transistor off and this transistor off. How is this done? Well, these are called gates here, here, and here. All right, those are gates, and if you set the gates to 0, that turns the transistor off. Now let's go see in addition to the 0, 0, 0, I also have a couple ones because the output of these positions here after one inverter are ones. So you can see that this one here actually comes down to here and turns this one on. In a similar manner, this one comes down here and turns this one on. Now, an on transistor means it's going to conduct. The conduction will be between the drain and the source of the transistor, which will mean that I have a connection like this. That will zero out the output there because I have a direct connection between Y1 and ground. In this case, I have a similar situation, and Y2 will be 0. But in the top situation, I have no zeroing at all. And the high that's over here will travel through and pop out over on this side. Now the lecture notes kind of discuss this, and let's kind of take a quick peek at that. Here's the case where you have 0, 0, 0, and all three transistors are off, and that produces that. Now, if one of the transistors is on, this shows you what happens. It produces a 0 here because I have a direct connection to ground, and that's a symbol to a ground. So that's how this works. All right, now let's do part of the blue case, and I will then have you complete the rest of the blue case by using your iClicker assignment. So let's go ahead and pick a blue color. There we go. And let's change the address from 000 to the next location of 001. Now, in the blue case, I'm also going to have a 0 here, a 0 here, but I'll have a 1 in this case, all right? And over here, I'll have a 0, all right? So in the first two columns here, we have identical situation. We have off, off, and off. In the blue case, I have a 0 that's touching these three gates, turning them off. In addition, these will also be off. However, because now I'm using a 1 here rather than a 0, these transistors will now be on. Hit this one and this one. And in addition to that, this blue 0 will come down here and appear here, turning this one off. So let's take a look at what we have here. All right. I have I'm going to leave this one here open here for you to figure out on the iClicker quiz. But I have, in the first row, I have an off, off, and an on. So that will ground this one, producing a 0. In the second case, I have an off, off, and off. Therefore, I have a 1 that's going to pass through and produce a 1 here. In the third case, I'm going to let you figure this one out. So how are we going to do this on the exercise? Well, let's take a look. I'm going to give you an example of one, and I'm going to have you figure out the rest of them. So in the red case, which is in the red box was associated with the red case, should I have asked you what are the conditions for the transistors and the output resulting from that, you would have said off, off, on, and then this 0 would have been appearing here. All right. So let's do it this way. Let's say that I have a space here, and I put a space also here, and a space here. So the answer, should I have asked you about this in the red case, you would have typed OFF space, OFF space, ON space, and 0. All right. So here's your assignment. I want you to, I've already given you part of the answer, and I can see that I probably should extend that rectangle just a bit more. All right. And whatever answer that you get here, and let's go back to the pen now. This is kind of fun to do, isn't it? So whatever output that you get here, I want you to write here. All right. So, and then put spaces here and space, well, let's see, a space here after the off, a space between this one and this one, so a space here, and then a space here. So let me just say SP, 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 okay? All right, so I want you to go ahead and complete this for your third iClicker assignment, and I'll give you some time to do that. Go ahead and stop the video and see if you can answer that. Remember that this output here is the one that's appearing over here. Okay, let's keep on going. So that's how a decoder works. And all the answers are actually shown over here, by the way, even the examples that I've given you. So what a decoder does, in the address of 0 selects Y0. In the blue case, an address of 1 selects the first Y, or selects Y1, and in the third case, the green case selects Y2. Now, let's go on and see what happens to the encoder. The first encoder that we're going to use is going to be in this kind of an arrangement. Notice I've got the red case, the blue case, and the green case coming in to work on this. Now, of course, this is complicated because I've got all three cases, so let's take a look at this on the artboard, but just know that I've got all the answers here, including the answers that could be appearing down here as well. For given Y, here's the answer coming out of here. So let's look at this again. Now this is a prom decoder. So let's first of all figure out what we have. We have a starting position here indicating the output of the decoder, indicating I'm going to select this word and deselect these words. Notice how the transistors are configured. I have a transistor, 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 and they are connected to these columns like this through either a fuse or no fuse. All right, so I have no fuse, fuse, no fuse, and fuse. This is an older technology. We're not going to have this one. We're going to do this one, but no iClicker exercise on this because I want to do the more modern case using charges. But let's go ahead and discuss what I do here. All right. So with a 1 here, I'm going to turn these transistors on. So that 1 passes through here, all right, like that. Turns this one on, turns this one on, turns this one on. And now a 0 to these two are going to turn them all off, all right? Which means they're not going to appear. Now for a technique that I'm going to use here, I'm going to just select these and then push them down. If I could, let's see if I can do that better. There we go. And these will all be off as well. All right. Now, an on transistor is going to make a connection. Since there's no fuse here, it will not make a connection. Since there's a fuse here, this will make a connection to ground. All right, so mainly showing that this output here will be a 0, and I will have a 0 appearing in this position. This fuse here is going to be grounded. It's going to conduct this line to a ground, so making this ground, so therefore this output will be a 0. Now, what about the two cases where I have no fuse? Well, the highs that are over here are going to pass through and appear down here, all right, as well as the high will come through here. Oh, see, I lost my one there, and will appear here, all right. Let me take these out here and just put the one here and the one here that I just showed diagrammatically how this worked, okay. So the contents of this memory is 10. The contents of this encoder is 1010. Now, I'm not going to pursue this any further except just to show you what happens if I put in the blue case and the red case. All right. In the blue case, I'm going to change this, and I'm just going to select now this word and deselect the first Y0 and deselect that. All right. So the answers are given in your notes, but basically I'm going to turn all these on now, and wherever I have a connection here, 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 and here, that will produce a zero here, a zero here, and a zero here, and in the blue, so I'll have a zero here, a zero here, and a zero here, and then there'll be a one here because I have no connection, and so that one will come through here like this, producing that one there. You see how I did a good job on that one. All right, so that's how this memory works. And for the green case, you can see the answer in the lecture notes, which is right here. All right, so the green case is going to be 0, 1, 1, 1. Let me check my answer. 0, 0, 1, 0, 0, 0, and 10, 10, just to make sure I did it right. 10, 10. Yeah, okay, I got it right. But this technique, fuses are no longer used anymore for an encoder. So as I explained earlier, we have different techniques, all right? So instead of using the encoder, excuse me, over here, instead of using fuses, all right, we're going to use something called a double gate MOS transistor array, which works with charges. So let's see how this works. And let's see, how am I going to explain this? Let me think about this for a second here. Yes, I think I'm going to go to the lecture notes and use this. Now, in the earlier case where I did use a fuse, I want to show you how it worked like this. All right, so anytime I had a fuse here, this fuse could be here or not here. And if I want to program it, I blow that fuse out. All right, the lines left and right are going to be words, and the vertical lines are going to be bits. So these were words going across, and these were bits going down. Now, an intact fuse connects to 0. So when the fuse is there, this line will be connected to ground, which is that. A blown fuse gets that one from the very top, as I had illustrated earlier, way up here, and then it comes down, and it's not bothered by this one. But you might say, wait a minute, it may be bothered, it may be affected by these other rows that are over here. Well, just remember, only one of the rows is selected and the rest of them are deselected. In the red case, it's just this one. And these cannot bother it because they're all off. So in the red case, you can see that only the first word is selected, and the second and the word 0 and word 1 and word 2. Word 1 and word 2 cannot be selected anyway. So now here's the new technology, and the new technology is the EPROM, which is actually one of the ones that I had discussed over here as well. I didn't discuss it, but I'm now illustrating it. The electrically programmable read-only memory. So here's how this one works. I'm going to use a decoder as I did before, so the differences are in the encoder. So for the encoder, we have a special transistor with two gates. So I have this blue gate, which is I apply 0 or 1 to, plus this red gate. It's called a floating gate because it's in between the top and the two blue lines here. All right. Again, I have a word and a bit organization. In the case where the red gate is not charged, all right, because this red gate can be charged or not charged. In fact, let's just say it this way. In the case where I have this red gate, I charge it or I don't charge it, and that gives me zeros and ones, as I'll explain in a second. If I don't charge it, all right, it's going to produce a normal transistor. The red gate doesn't have any effect on the blue gate, and so therefore, when I select this transistor, this will ground that output, all right? But let's compare these two. Should I charge this and I charge it negatively, this prevents this transistor from going on. Now, it ordinarily would be on, but if I charge it, it's going to stay off. Well, an off transistor will not affect the line, and so that one that started way up there on the top, like I showed several times already today, will appear over here. All right. So that these two here are going to illustrate how we work this problem together. So here's the encoder array with using charges. So the charges are, you can see there's a charge here, a charge here. So that's going to represent different outputs. So let's just go ahead and do a little quick demo of this. I think you can see how this works. So let's go to the artboard and go to the EEPROM, electrically the erasable PROM. By the way, it's erasable. Let's back up on that here. It's erasable because if I shine ultraviolet light on this through a crystal window, all right, I can remove these charges. It's pretty cool. And that is illustrated in these diagrams up here. These memories here have crystal windows that I can shine ultraviolet light to get rid of the charge in the arrays. Okay. By the way, as I'm going down the line here, this has yet been replaced by another technology called the EEPROM, which is electrically alterable PROM, and that's the predecessor to even another technology called a flash memory. So we're still back a few years ago. You have something even more sophisticated than what I'm showing you here, but this is close to what you have. All right. So what I'm going to do here is show this on the artboard, and here we go. So here's an artboard showing the cases that I'm illustrating. So let's go ahead and see if I can turn these transistors on. In this case, though, I've got a charge here and a charge here. That will keep them off. Now let's just go ahead and do this. And I'm going to put a circle around it and a circle around this. And now these two transistors, because they see the one, they'll turn on. All right. Now, all the other cases are going to have a normal off. Now, see if I can do this massive off swing here better than last time. Oh, this time I did it right. Okay, I'm happy now. All right. Now, the reason I have a circle around these two offs is these offs were due to that much charge. These offs, these 8 other offs, are due to the fact that I didn't select them. You see the idea? Oh, now you're beginning to understand it. I see. That explains that selection earlier that I was doing. So sometimes doing 2 examples will kind of show what's going on. So what's the result of all this? The offs here are going to prevent any contact. The on here is going to ground and produce a 0 here. It's going to produce a 0 here. That 0 will fall down and go over here. All right. So I'll have a 0 here. Now the rest of these here are going to get the highs that I've done before and will pass through producing a 1. All right, so that will produce a 1 here and a 1 here. All right, so we're ready to do an iClicker exercise on this, and I'm going to turn the exercise on. Let's see what it is this time. Okay, so what I'm going to do, we never talked about the green case in any of these examples here. All right, You might remember what the blue case was. We did do that one earlier. And so I'll go ahead and give that to you because we can do that. Let me switch to the blue color. And so anytime there's a minus charge, that's going to produce a high. So I know that in the blue case, it's going to produce that, and it's going to produce this. Oh, I'm showing you the trick now how to solve this. So in the green case, what you can do is look to see where the charges are. Here's the green case. Oh, here's the green case. Let me do that. That'll be 0. Well, the blue case was this, and the green case is this. All right, so we're going to be working with this information here. And so wherever there's a charge, that will produce a 1 here. So go ahead and now this will be your fourth. This is your fourth iClicker assignment problem. Go ahead and go to that problem and fill in the answer for that for the green box here. I'll give you a second to do that. Okay, so now we're ready to do our last idea for this session that we're having, and let's do that now. Let's go back to the notes, and now I'm going to talk about those flash memories. Now, there's some links here that will dig in and explain how those flash memories actually work. Remember what the progression is. Let me go back up here to explain how this works. It goes from the read-only memory, which where the manufacturers do it everything, and then the programmable ones where you could program it using a PC, but then it's no good after that. And then the erasable proms where you could erase it as well as program it. The EEPROMs, I'm kind of skipping over that. That was in between the EEPROM and the flash memory. So the flash memories are the ones that you're currently using. If you have one in your pocket or in your purse, it's a flash memory. All right. So the flash memories can be explained from these links. Now, because I'm going on here and you want me to probably finish this up, I'm going to not discuss the details of this, but you can click these links and learn about them. They use the same double gate implementation that I've been talking about earlier, and I think I will have an opportunity to bring it up maybe later on in another class. But let's go ahead and explain how this one works. I'm going to show this in the contents of what you're using in the laboratory. You know that you program the Basis 3 board, and it has a chip in it that contains all the information. So that is actually programmed with a bit stream, and those bit streams basically put charges in the encoder, and that's how you get the zeros and ones. But in particular, what I'm going to do here is show you a little bit more advanced scenario, and that is the following. Suppose I had a situation, which is what you have in the laboratory, where you want to generate logic functions, which are sum of products. Now here I've got a number of products, and I have n inputs to each of these. And so if I OR those together, I have a sum of these products. Now, this formula can represent any equation that I want. And so this is the result of something that is programmable. All I need to do is program this. I can keep the same structure no matter what the problem that I have is. All right. This is called a programmable gate array, or PGA, not to be confused with the Professional Golf Association, which some of you will have to wait a little longer until next year to get into that again. So the programmable gate arrays, it says down here, will sum P products that we have over here. And each of these have n inputs and also n negated inputs. So basically 2 to the n such lines. So let me show you an example of that before the rest of these are explained. I'm going to show you a programmable logic device that has 2 product terms and 5 outputs. All right. And it doesn't show it here, but I also have n is equal to 4 or 2 times n is equal to 8. So let's look at this. So here what I have is a general, and I've got 5 examples here to show you. And then your final iClicker here will be to solve a sixth example, right? So the idea here is that I'm going to have two product terms or two AND arrays. The arrays are then connected to these 8 inputs. There's really only 4 inputs because it's input I1 and its complement, as well as I2, I3, and I4. So it's 2 to the n times 8, but they like to explain it like this, to set this up as an array. Now this single line here is actually 8 lines. So it's a artistic simplification. The 8, in this particular case, it's showing that I connect 4 of the 8 lines to these positions here, and I don't make any connections to these other ones. So in this particular case, this produces I1, I2, I3, and I4. Now the bottom case connects not I1 and I1, and that is down over here. Now the purpose of that is to put a 0 on the bottom. So the net result of this is that I've generated an AND gate. All right, so I can generate an AND function with these dots. I can generate an OR function just simply by dotting I1 and I2 to produce this. I can do a NAND function by ORing not I1 and not I2 and noticing that not I1 or not I2 is actually De Morgan's law. Okay. And by the way, I got to explain what these dots, how these dots are done here. I hope I don't forget to do that. The NOR function is done with not I1, not I2, not I3, and not I4 ANDed together by De Morgan's law. That's equal to this. Isn't that amazing? Aren't you glad that you learned De Morgan's law in the beginning of the course? And the exclusive OR function is going to be I1, not I2, not I1, I2. That's the algebraic expression to this. And so here is I1 and not I2 and not I1 and I2. Now, what are these dots? These dots are the charges, all right, in those red gates, essentially, all right. That's where the connection is done with this, all right. But I'm also not only doing charges and setting up a memory, but I'm actually connecting the memory into a programmable logic device. So I've jumped ahead of your one in your pocket and one in your purse, however you're carrying these. I'm going beyond that, and I'm actually going right into your laboratory now, because this is the way that your laboratory actually functions. All right. And I'm going to, for purposes of shortening this discussion, I want to explain that this one had 8 inputs. It had 2 product terms and 5 different examples. The one in your laboratory, all right, let me just kind of show the final result. All right, it has 960 inputs, 160 outputs, all right, and it has um, in one of these boxes. So you can, if you compare this box here, you see that square there, all right, and then a bunch of inputs, all right, that's one of these squares over here, all right, and there's actually turns out to be 960 inputs into each of these here essentially, okay? So, and then you multiply by 2 because they include 2 of these structures which are called slices. All right, so let's go ahead and do an iClicker exercise to finish this up. You can see that I'm done with this subject. And what am I going to ask here? So let's go to the artboard. Do you remember now how to do these 5 cases? I'm going to ask you to do a different case. So here it is. So here are the 5 cases that I have here that I've demonstrated just as before. It's the same art. All right, but what I'm going to do now is I'm going to fill in one here, and I'm going to, and let's just see how this works. Let me before I explain what it is, I got to remember exactly what I have here. All right, that's what I'm going to do. So it's reverse. It's kind of a reverse problem. What I'm wanting you to do is I want you to program this AND array, and we call it an AND array because these are the connections to this and this AND. I want you to program these with dots, all right? And to produce this function, I1 and I2 or I3 and I4. Now, the way to do that is as follows. If you look at this example up here, this dot here was connected to I1. Well, this is an interesting gate. This one here has both the I1 and the not I1 on the single gate. Well, that's a shorthand artistic symbol actually, but let's go ahead and use it. This dot indicates not I1, all right? So using that key, place the dots here, and we're going to represent the following in the green color, all right? So let's do this. A dot that you use in here, okay? A dot will represent as a 1. No dot, all right, will represent a 0, all right? So let me put a box around it here, or a box around here, so you can see there's no dot there, all right? So what I want you to do is for every position that you have a dot, put a 1 there. Any position that you don't have a dot, put a 0 there, all right? And this is your fifth and final iClicker assignment problem. And the due date on this will be given on an email, as I don't want to put a date on this in case I need to use this lecture another semester. I don't want to be giving dates at this point in time. I'm a smart professor. And I see that maybe I can use this another time for another exciting class of digital logic. So I hope you enjoyed this video and that you can solve these 5 problems. We will hopefully see you soon again in the lecture hall.